out on a new chapter, and as I said once before, every time we start out with a new chapter, there are some new ideas that we begin with and then build on up from there. So let's look at a theorem or two and see how it might go. Oh, let's state this theorem, and perhaps we would like to prove one or two little parts of it. For every real number a and b, right, for every number a and b belonging to the set of real numbers, and for every number m and n, say, belonging to the set of natural numbers. Now, I think all of this notation is quite clear and meaningful to you. Let's see now. Let's look at a to the m times a to the n. And before we actually come to the conclusion of what this is, I think you all know what its conclusion is. Let's actually try to prove it and see where it will take us, all right? If we were to look at a to the m power, where m is a natural number, you and I have been saying that this means a times and so on times a. Is that right? And how many of these factors of a do we have there, Steve? There are m factors of that number a, and then times, and then we have a times, and so on to some number a here. And then how many of these n factors do we have? But Steve, we have indeed n of them. And notice then that we have the product of these times the product of these, and then just removing our parentheses, so to speak, we then will have the product of these, and therefore how many will we now have? And Glenn says we then have m plus n factors. And now going right back to what the definition of m plus n factors is, what then do we mean by this? But a to the m times a to the n then is going to be equal to, and Kirby?
A to the m plus n.
A to the m plus n power, all right? In which if we were multiplying two numbers of the same base, notice then that we will add their exponents. And I think that this is certain property that you're familiar with. Well, let's look at a few others. Rather than proving all of these, suppose we were to take a times b and raise all of that to the mth power, say, then we may conclude that this is then going to be equal to, and without going through all of the details of this proof, Dick?
A to the m plus b.
A to the m times b to the m. Is that right? A to the m times b to the m. And let's see now, I think there's another theorem, another one of these properties or laws as the book calls them. Let's talk about a to the m power all raised to the nth power. And thinking of this, we're taking a power of a power, and what then does our theorem tell us, Doug?
A to the mn.
This is a raised to the m times n power. Is that right? Well, let's see now. There are some others which we may state. If m is greater than or equal to n, then a to the m power divided by a to the n power, we would like to say is going to be equal to what? And Glenn?
A to the m minus n.
A raised to the m minus n power. Now notice here, we started out in our original statement that m and n belong to the set of natural numbers. And we would like to have our answer in terms of, or the right-hand side, the result of our theorem, to be over the set of natural numbers. And now notice here in this case that if m is greater than n, certainly m minus n is still going to be a natural number. But notice also in the case in which m is equal to n, we then will have a to the m divided by a to the n, then as we're saying is equal to a to the 0 power. Is that right? M minus n would then be 0. But we have already defined a to the 0 power. Notice it was a definition. And we said that it was equal to, Steve, is equal to 1. Okay. Well then suppose we had the case in which if m is less than n, then what can we say? We have a to the m divided by a to the n. And again, we insist that we end up with a positive integer here. And Steve says
1 over a to the n minus
1 over a to the n minus m power. In this case, now n minus m is then going to be positive. Okay? Well, let's see what else we may say. Suppose the number b were not 0. If b is not equal to 0, then we may say something about, say, a to the m power divided by b to the m power. And what then would we like to say that this is equal to? Bill?
A over b all to the m power.
A over b all raised to the m power. Or in fact, perhaps one could write it starting out with a over b all to the m power. It then would be equal to a to the m divided by b to the m. Well, there's another statement in which we may, let's write it in the following way. If the number a A does not belong to the set of numbers negative 1, 0, and 1, alright, then a to the m power is equal to a to the n power if and only if, let me use this double F notation that we have used once before, if and only if what is true about certain numbers here. And that
M equals N.
if and only if m is equal to n. Now notice here what it enables us to say is that two numbers are going to be equal in terms of whenever they are in terms of their powers. For example, 2 to the third power is equal to 2 to the third power if and only if 3 is equal to 3. And certainly that would be true. Now suppose a were the number negative 1. Negative 1 to the, say, to the fifth power is equal to negative 1 to the seventh power if and only if 5 is equal to 7, and that would be false, wouldn't it? So that's why we exclude the number negative 1. I think similarly you would exclude the number 0 and also the number 1 for the values of a. So if you exclude those cases, indeed this statement then will always be true. Okay? Well, there are a number of theorems here, certainly. We've proved only this one part, notice, and in fact we could go through the proofs of these others, but I'd rather not do so at this time. Let's look at another theorem. And again, all of these theorems are simply to help us be able to do some of our manipulation and to be able to simplify expressions for every A and B and C and D belonging to the set of real numbers, where C is not 0 and D is not 0. Let's exclude those cases. A times B divided by C times D, you would like to say, is equal to what? And, well, Doug? A over C times B over D. Notice in this case you would like to separate these numbers in some way. Well, let's actually go through the proof of this, in which here is our statement and the reason for that statement, and let's see how it might go. Well, let's just start out here with the left-hand side, A times B divided by C times D, and let's just go right into that property which enables us to write this in this pattern. And what's our reason for this? A over B, AB divided by CD then is equal to AB times 1 over CD. And Don?
Relationship between multiplication and division.
Very good. The relationship between multiplication and division. So let's just abbreviate here the relationship between multiplication and division. Now, way back where, perhaps back in chapter 1 somewhere, there was a statement which enabled us to look at 1 over CD and rewrite it as 1 over C times 1 over D. And perhaps you wouldn't remember the wording that we've used. Certainly I think you would accept this statement that we have here. But it has something to do with reciprocal of products is what it was called. So let's just indicate that the reciprocal of products will enable us to make this statement. And now looking at this, you say to yourself, well, I can use our commutative property, I can also use our associative property and regroup things, and I think without too much trouble you can get to the point where you say, well, I think I would like to write this as A times 1 over C times, and then finally B times 1 over D, and our reason for this is just as I said, our commutative, let me just abbreviate, and associative axioms with respect to multiplication. Now, right there then, what's the object of setting it up in this pattern? And you look at it and you say to yourself, another name for A times 1 over C is what? A over C. So let's just indicate that. Times, and here a name for this is what? B over D. And again, what is our reason for this? And we're just using the same idea a second time, Tim.
Relationship between multiplication and division.
There again is our relationship between multiplication and division. Are we done? Have we proved this little theorem? We started out with AB divided by CD on the left, and by a process of our reasoning based upon other theorems and what have you, we certainly have ended up with the conclusion that we want. Let's indicate this as step 2 and 3 and 4. Perhaps one could put in a step 5 and conclude that therefore the left-hand side then is equal to the right-hand side. And what would our reason for that be if we had to give a reason for that, Doug? That would be the transitive property of equality. Well, there are one or two little corollaries that we may look at as a result of this theorem. For every A and B and C and D belonging to the set of real numbers, again, let's exclude the case in which the denominators are 0. All right, let's see now, what may we say? Looking at our theorem, suppose we had AB divided by C. And in other words, some number here in the denominator is equal to 1, and C times 1 is C. And I think you would agree that we may rewrite this as what? Well, let me just think of A times, and then what would our conclusion be, Malcolm? B over C. I think this would be a direct consequence of the theorem. And suppose also we took simply A divided by CD, in which you look at this and you say, well, this is really A times 1, or 1 times A in the numerator. And using the same theorem, we may rewrite this as what? And
1 over C
1 over C
times A over D.
times A over T. Okay? Well, from these theorems, you can go on and look at some others. Perhaps another idea that we could look at, which in fact we should, is a definition. Thus far, notice we don't have anything about negative exponents. And for every a belonging to the set of real numbers, where a is not 0, and for every n belonging to the set of natural numbers, suppose we were to write a to the opposite of n. And this is a definition, notice. What would you like to say that this is equal to in order to be consistent with everything else that we've said here?
1 over A to the
1 over a to the n. And again, notice that this is a definition. Now, immediately from that definition, I think we can look at a theorem which says the same thing for every a in the set of real numbers which is not 0, and for every natural number n. Now let's start out with 1 over a to the opposite of n. Suppose you had a statement written in this pattern. What do you think that you would like to say that this is equal to, Rick?
A to the N.
This then you would like to conclude is a to the n. Now most of the time in our problems and in our exercises and in our simplifications, we're more concerned with positive exponents. And in this case, if n is over the set of natural numbers, then the opposite of n then is going to give us a negative integer. And if we would like to write it in terms of a positive integer, we have this statement right here. Well, I think the proof of it is very straightforward, but let's indicate it. Here is our statement and our reason. And in fact, that's probably a little two-stepper, in which if we were to start out with the left-hand side, let's use the definition of what is meant by a to the raised to the negative n power, or the opposite of n power. And that's our definition that we have just stated above. Right up in here, we have a to the opposite of n equals 1 over a to the n. And now how may we use that in this statement, Don?
1 over A to the N.
This then is equal to 1 divided by 1 over a to the n. Is that right? And this is our definition of a to the opposite of n. Now, just looking at this right-hand side, all right, how may we then think about that? What's another name for 1 over a to the n? Which has to do with some idea. What did we call that? This has to do with the reciprocal. Isn't that right? And going right from what is meant by the reciprocal, give me another name for the right-hand side here. And Dick?
A to the N.
This is simply a to the n. And what you're using there is simply the reciprocal of what? 1 over a to the n. What's the reciprocal of 1 over a to the n? A to the n. Is that right? And so in one step there, you indeed have shown that 1 over a to the opposite of n then is equal to a to the n power. Well, these are a number of theorems, and I think perhaps it's worth our while to look at a few examples. And let me pick out some examples that we may do and rely on these theorems. Again, as we do these examples, I would rather that you do not put in every little gory step, every little detail of step as you're going along there. Oh, let me just make up some problem here as we have in this pattern. Well, let's see now. Let's write our next line right here. And looking at this, you say to yourself, well, I just see the first theorem there probably, in which we also have a negative 2 times a negative 3 factor to worry about. And this then is equal to, who would like to write down our final result right in here? Kirby?
6,
There's 6.
A cubed,
A cubed,
B cubed,
B cubed,
C cubed.
C cubed. Very good. Is everyone agree with that? And in fact, perhaps someone else would like to look at that and say, well, it's 6 times, and using one of our other theorems, I wouldn't say that this is a more simple name for it, but certainly it is another name. And what then may we write here? Something in the pattern, Dick?
A times B
all cubed. Is that right? Using one of our other theorems that we have just established. Well, look, let's look at a few more examples. Suppose we had negative 2a squared all cubed times, and suppose we had 3b squared c to the negative 1 power all squared. And let's look at this. And now notice here we are using one of our theorems in which we have negative 2a squared all cubed is then going to be what? Give us another name for this, Don.
Negative 2, 8,
Careful, it's negative 2 cubed that we are concerned with here, which is negative 2 times negative 2 times negative 2, which is,
negative
there's a negative 8, a to the 6th power, is that right? Because there we're taking a squared all cubed is a to the 6th, and then times, and now let's look at this factor on the right-hand side, and who would like to give us another name for it, Brenda?
9
There's 9
times b to the 4th
b to the 4th
times c to the negative
times c to the negative 2. And now notice in this case, put in as many steps as is necessary for you to be able to follow your work. And now looking at this, we see we're almost back to the same step, for example, as we had in problem number 1, in which we have negative 8 times 9 is, what then may we say? Well, who would like to give us an answer here, Charles?
negative 72,
Negative 72,
a to the 6th,
a to the 6th,
b to the 4th,
b to the 4th,
c to the negative 2.
times c to the negative 2. If we insist upon writing our exponents with positive integers, rather than thinking of this as times c to the negative 2, what else may we say here, Tom?
over c squared.
All divided by c squared. Let's write it in this pattern, shall we? Very good. Well, let's look at another example. Suppose we had a problem such as this. 3 times a to the negative 2 power b squared all raised to the 2 power divided by, say, suppose we had 2a b to the negative 3 all cubed. Perhaps this is a little bit more messy, and let's see what we can say. Again, we're using the same theorem as we used in problem number 2, in which we have 3 times a to the negative 2b squared all squared. So what then is another name for the numerator? Let's just take it one step at a time. Someone who hasn't said anything here, go ahead.
9a
9a,
to the negative 4th,
negative 4,
b to the 4th,
b to the 4th, all divided by, is that right? And now let's look at our denominator, and someone else, Malcolm? We have here 2 to the 3rd power is
8a cubed,
8a cubed,
b to the negative 9.
b to the negative 9. Does everyone agree that it's negative 9 there? And now let's look at that, and again, let's write numbers with positive exponents. And looking at it, you say to yourself, well, I have b to the negative 9, and using our theorem, which we have just proved, that's really 1 over b to the negative 9 is another name for what? B to the positive 9. So let's then write here, we have what? 9 times, now let's put a to the negative 4 downstairs, so to speak, and what is left in the numerator? But, well, anyone? Bill?
b to the 13th.
b raised to the 13th power. Does everyone agree with that? b to the 4th times b to the 9th is b to the 13th. And then finally in the denominator we have 8 times what? a to the 7th power. a raised to the 7th power. And this is probably the most simple name for this expression. Okay? Well, let's look at another example. I think that's probably all that we need to do for today. Suppose we had 4x to the 4th times 3x all cubed and minus something. Suppose we had another factor here of 2x cubed all squared times the 5x. And let's look at this and see what happens. Notice here we have one term minus another term, in which you may work with what we have just done in terms of this form and do the same thing with that one, and possibly you can take their difference. So who then would like to give us another name for the first factors here? Don?
12x.
Again, I think we have to be very careful here. Let's put in another step of 4x to the 4th power times something. Now here we have 3x all cubed. And I purposely selected this example because this exponent of 4 applies only to the x, but this exponent of 3 applies to whatever is inside the parentheses, namely 3 times x. So Don, what then would you like to have for the other factor? 3 cubed is 27 times x cubed. Well, let's just indicate that, minus, And now let's look at this. Perhaps we had better put in 2 steps here again. And Dick, what would you like to say for the first factor?
4
We have 2 squared is 4
x to the 6th.
times x to the 6th power, is that right? And then times 5x. Well, let's then see what this is equal to. And here we have now 4 times 27 is 108, is that right? It's 108, and the x to the 4th times x cubed is x to the 7th, and minus, and here we have 4 times 5 is 20, x to the 7th, and you say, the problem is rigged, because now we can take their difference, is that right? These are like terms, and therefore we may say that this then is going to be equal to, and what's our name, Peter? 88 x to the 7th power would then be the most simple name for this given expression. Well, let me give you your homework assignment. This will be assignment number